Okay, I think we can kick off. Let me introduce you to our community. Hello everyone who joined this call. I really appreciate that you guys found time to join this talk today. At Bugout, we really do our best to, first of all, to invite great speakers, to bring this interesting content like what's going on in cutting-edge research, but also we want to create supportive environment for everyone, supportive in a sense that to bring the sense of community, that we all here to learn from each other, to support each other in any ways we can. And if you're not part of Bugout Slack, please join. I will post a link to our Slack shortly. So today our guest is Sahica Genç, who is a principal applied scientist at AWS Artificial Intelligence. Her research mainly includes reinforcement learning, smart automation, and maybe Sahica will share more what exactly like she's focused on these days in her research. And today specifically, she will introduce DeepRacer, a product that she's working on to help accelerate research in reinforcement learning. So if you're interested in reinforcement learning research, this is a talk for you, and you will learn how to use new tools that will help you to get started with reinforcement learning. Sahica, thanks a lot for your time, and we're very much looking forward to hear from you.
Thank you. Really appreciate the introduction.
I had some extra slides. What I'm going to do is that I'm just going to share my slides with Sophia afterwards, and so you'll be able to learn a little more about things that I wanted to discuss in between. Apologies for that. So what I wanted to share, basically my main theme for today was that while software, while finding bugs in software has been very critical and has been well studied, and as you are one of the communities also supporting to find how you can improve this process and learn from the user experience. One of the areas that has not been as well explored is when the software is touching devices, or what we call hardware assets. And that is one of the things that I wanted to bring out of this presentation, and hopefully give you some ideas about how we've done it and how you can potentially help the others around the world, and try to figure out how we can better learn about bugs and potentially software issues that where the software is actually touching the devices. So one of the, as I was mentioning, AWS DeepRacer had started with us trying to kind of reach a bigger community to teach reinforcement learning and democratize reinforcement learning in both in production, and also bring it to the hands of the solution architects and engineers who did not really had the training and the doctorate and degrees that that they could go through to understand the theory behind it a little better. So our goal was that how can we do this in a fun way? And we started with a toy car and a league, where we just, what we came up with was that we're going to put really cutting edge AI on this toy car, and that if we can make it work on a toy car, then it may be easier for people to understand how they can apply it to their business problems. And it got really big. Last time we actually did Reinvent in person. This DeepRacer was one of the most tweeted topics, and we had a lot of participation from around the world coming to Reinvent at AWS. And I provided some statistics here that how we were able to build a community around it, and they helped actually find some bugs, and that we actually learned from them. As usual, what I would like to say is nothing starts simple. When we first started this from day one, we decided that we need to have started working on the hardware from day one. We didn't separate the development between hardware and software, to be honest. That we said they're all going to start at the same time, and we will evolve the hardware, we will all evolve the software as we learn from one or the other. And as you can imagine, at some point, my desk was full of toy cars, and that there are some components of it. And if you're familiar with toy car racing, you would also see these are actually donkey car frames. And no, I didn't have coffee at the time in my mug, so all the electronics were safe. So there is a big journey when you're putting software into a hardware from getting from this environment into a product. And I do strongly believe that there are a lot of hits and misses in this round in terms of finding bugs and providing an AI on device that is relatively safe. So when we first started, that we had really big aims, that we thought that we're going to do this, we're going to have a real racing like you're seeing Formula One, we've learned to drift and so forth. Our dreams were quickly crashed. What we learned was that toy cars do not actually pose toy problems. One of the things that we learned was it was a good thing that we started with the hardware from day one and experimenting between the software and the hardware. What we learned was that as opposed to hardware devices that you would have in industry, we didn't have Six Sigma. And we learned that many of our devices has come with some different servos. They come with this different motors, and sometimes it's difficult to gauge whether the wheels will be turning the same and so forth. So our dreams were quickly crashed. And one thing that we learned is unit test is very important. Let's start simple. Let's start with some simple tests. Can we go straight? Can we turn? How well we can turn? What are the angles we can turn? So I'll give you a few videos here. So when we first started, as you can see, we can barely go straight. This was one of our first experiments. And then we started, we found some bugs in our initial testing, and then we went back and improved those. And now you can see we can actually go straight. And at all these times, our algorithms are driven by reinforcement learning algorithms trained on AWS services, which I'm going to touch later in this topic. And as you can see, then from there on, this is where we wanted to be. And we started by testing really small and have step-by-step from software to hardware to software to hardware in order to go from here to here. Who could have imagined going straight would be so difficult? So in the next part of the talk, I'm going to talk a little bit about what reinforcement learning is. I'm going to cut a few topics a little short, and then I'm going to jump a little bit further ahead in my presentation to give you an idea about how we actually had started testing things. Reinforcement learning actually is not a relatively new topic. It has been proposed in the 1950s by two prominent researchers, Sutton and Bartow. And most of you who actually search for reinforcement learning will see that the book they had written over the last year, which was updated over the last couple of years, is kind of the Bible for reinforcement learning. It started in the 50s as they were thinking about trial and error learning as an engineering principle. And you can also think about this as we try something, it fails, you find the bugs, you go back. And then they started thinking about how we can theorize it and put formalizations around it so we can scale this approach and learn how we can apply it. And it was first applied to optimal control through dynamic programming. So at the time, most of the things around reinforcement learning actually depended on building models from first principles. And then in the 80s, it made a comeback as part of the optimal control. So one of the things in optimal control, when I was first taking my optimal control class, what I learned is that engineers were trying to learn about how they can maneuver a plane for high altitude flight. And what they learned is that they were keep crashing and crashing and crashing. I mean, sometimes literally, unfortunately. But what they had learned was that when they put the problem into an optimal control setting, what the plane has to do, given its dynamics, is it has to dive a little bit before it can climb up to a higher altitude. So optimal control kind of opened the path towards maybe some control problems are not as trivial as we think, that we cannot just pitch the plane to go up. We actually have to pitch it down before we can start climbing up, given the physics. And hence, with this new realm, reinforcement learning came back in the 80s, and it became modern reinforcement learning, and now combined with optimal control. And more recently, about a decade ago or so, DeepMind came out saying that, well, you know, the models that we had been creating from first principles, with the deep learning now becoming mature, we can actually learn these models from all the data that we can collect, either from simulation or from actual data. And this was kind of the rebirth of reinforcement learning. And in our case, what we were doing was that we wanted our car to learn from a driving environment, first in a simulation environment, and then from simulation, we wanted to apply it to a real world. You can imagine that you can think about this first. Why don't you learn in the real world? And initially, before AWS DeepRacer, we were doing robocar racing, where we actually applied behavioral cloning, and we were collecting data in the real world. But what we had learned is the data that you collect in the real world, your behavioral cloning is as good as the data that you learned. However, in real world, you may not always have good drivers that you're getting the data from, and or the driving styles may be different, and or you're not actually learning about all different kinds of environments because you have limited time and space and money to collect all these high value experiments. So our goal from start was, how can we exploit using the simulation as much? And what we also learned is that we would like to start with we don't want to reinvent the policy optimization techniques that has been well studied and applied in many gaming problems, more specifically Atari, and then later to other robotics problems. That what we want to do is we would like to pick the brains of these luminaries and really create a solid application out of it. But as we started picking up what we got from literature, what we realized is that there are sometimes we were getting really good results, sometimes we weren't getting really good results. So again, unit testing became really important. So one of the things that we learned quickly is that the agent's neural network that approximates the rewards is really related to the reward functions that we were creating. So the reward functions are kind of the human part of the reinforcement learning, in the sense that you can actually throw any neural network to it, but the reward function is something the person who's trying to solve his or her business problem, they have to build this reward function by themselves. And when we first released DeepRacer, we learned that some people were creating very simple reward functions such as stay on track, go as fast as you can. And then some people were creating really complex reward functions, and they were looking for, if you come to a turn where it is really sharp, try to cut across it, because that's actually where you gain some timing. And you actually go to Reddit, people are sharing these reward functions online, and we started testing out some of these very simple reward functions that are just few lines of code versus some other reward functions that are 30 lines of code or so. And it has more domain knowledge built into it. And we started learning backwards from there that our neural networks were actually containing quite a bit of information. With our new DeepRacer device, we not only put cameras, but we also have a LiDAR you could use. So our neural networks can get pretty complicated, that we have these 2D CNN image embedders. In parallel, we have 1D dense LiDAR data. And then we have a middleware where we combine this into a fully connected layers. And finally, we have the action output, which provides the probabilities for these actions that the reinforcement learning approaches picks from, whether through exploiting or through exploring. And we had done many tests. So we went to the lab. We first started out on the AWS DeepRacer software stack, testing these simple reward functions against different kinds of networks. So this is kind of a for blocker in the sense that you have in this column simple reward functions, which are mostly nonlinear. Stay on track, don't go as fast as you can. And then what we call advanced rewards function, take advantage of the curvatures, take advantage of getting closer to the inner lane because that's the shortest path. So what we have learned is that there's actually a trade-off between the neural network size that you could use versus simple reward function. And you know what happens? Depending on you choose shallow or deep, it also it changes how long you're going to train these networks, as well as how much money you'll be spending to get a really good result. So you can see in this case is that you can go with deep neural network architectures where you can get higher rewards. But in some cases, when you start really engineering your reward function, you can get a similar result with shallow neural network, and you can keep your training very economic in terms of spending and computational time. So again, testing in real world, testing in real world and testing in software is really, really important, and you have to go back and forth. So our next thinking was, all right, now that we know these neural networks are doing really well in the software environment, in the simulation environment, and that we know how to kind of merge these shallow network versus advanced reward function, or deep neural network versus more simpler reward functions. How can we really test before going to the actual world that these are doing really well? Because there's a huge gap between the simulation world and the real world, in the sense that there may be some obstacles, there may be some things that our simulation environment didn't really account for. Again, unit tests, really important, not only to find the bugs, but also to make a good product that you spend most of your time testing. And this is why it is really important to have a community around that you can help you build these unit tests, and not just confine it to the testing that you personally can do. One thing that we quickly did was that, why don't we go out and collect data? Because from day one, we started the hardware and software at the same time. And we started with like simple straight lines versus more complicated tracks. So we started using these GradCam analysis, and thank goodness for the community and the academic community, as well as as well as the engineers and practitioners putting out these available tools out there. What we started doing was we put some unit tests on the hardware, so we can collect image data and we can push them to the cloud, and we can then run our neural networks on these data that we collect from the actual world, and then compare it to how the neural network is seeing the actual world versus the simulation world. And here are some examples that these four images are coming from different neural networks that we had trained. And as you can see that in some cases that our neural network is able to capture to see the yellow lines, and so the warmer color means that the car knows that it needs to avoid those. And it can actually learn from these lines. And in some cases, it can actually learn really well. And this actually is coming from an attention transformer-based neural network, which is using attention part of the transformer in conjunction with a CNN. So it can actually learn a little bit better that this guy may think that it's okay to go outside here because there are more warmer colors. But this neural network is saying, no, those are no, you're going to lose the competition if you go out. Similar here that this neural network is saying that, oh, I mostly should stay around the yellow lines, but for some reason, if the mechanics don't work well, that it's okay to be in here. But the reality is, no, we don't want to do that. So it really was important. It really became really important to create a good product that will scale to thousands of cars and thousands of models across the world, that we had to go back and forth between hardware, software, debug it, collect unit tests, data from unit tests, go back and forth, and most of our times were spent doing this. And then things started getting better as we learned, and that most of the time that we weren't learning as much from trying different kinds of neural networks, but trying each neural network on the car, going back to the car, going back. And then we started exploring with different kinds of environments. So we started putting, what about, we have a darker place where you have some flashlights here. Is the car ignoring these, learning about these? What about these different colors of light? So again, the goal here is not just do it on paper, go back into the real world, collect data, back and forth and back and forth and back and forth. And here is a test that you can see that we're actually getting better doing that. So another thing that we did, for example, another unit test which was really helpful to us was, I mentioned here the action output actually is probabilities. We actually put these probabilities into our interface here, web-based console interface. So when we're actually running the car, we can click a button here and that we could see the probabilities changing. And you know what? That was one of the best things that we did, because we realized that when we were building our software for the network optimization on the hardware, on the chipset that we had, we missed the version on one of our libraries that we're using. And we realized that the probabilities were fluctuating a lot. The car was, by some miracle, doing the right thing. So this speaks a lot to the robustness of the neural networks and the algorithms. But having to output those probabilities and seeing it one by one with the camera stream as well as it coming out also helped us to realize, wait, why it is fluctuating a lot? We did not see this in the simulation environment. So we quickly realized that one of the libraries that we were using for building this optimization, building this optimized neural network on the chip wasn't actually the latest that we should be using. So now another test, couple of years ago, we ran a competition at NeurIPS. And now you can actually see the car is becoming really, really stable with respect to going through different environments, even within the same track. So here we're going from the regular track to a different track where it doesn't even actually have the yellow line. I'm going to skip the multi-agent racing. And what I would like to go to is that how you can help us. And how to get started. So how to get started on AWS DeepRacer, and this is where we can actually use your help a lot in order to make this an even better product for the AWS DeepRacer community. And I strongly encourage you that there's currently a Slack community that is actually run by volunteers, not by Amazon or AWS, but it's a huge community, and they share a lot of bugs, best practices, user experiences, and there's also a Udacity course that you can join to learn about AWS DeepRacer. Now, I want to say that the software stack behind AWS DeepRacer on AWS is very complicated. But the good thing is you don't have to go through this complicated process. If you are just starting it, we made it really simple for you. You can just get started with the DeepRacer console where you can have very simple reward functions, and then you can see how you can use two different kinds of reinforcement learning approaches. But in general, that this is a very complicated infrastructure where we have AWS RoboMaker, which is a cloud robotics simulation. In this simulation environment, we can actually have multiple rollouts, meaning that we can have multiple tracks, multiple environments that the car can learn from. And then we have Amazon SageMaker. This is Amazon's machine learning, Amazon's machine learning AI toolset that you could utilize for deep learning and or deep reinforcement learning. Use a simple Jupyter Notebook environment, and or you can use SageMaker Studio for Jupyter Lab. What it does is it actually talks to RoboMaker, so you can decouple your training from your simulation environment, that you can have one instance or multiple instances running training while you have several multiple instances that you're using to create new experiences from the new networks that you learn from. And finally, I think you would like our CloudWatch a lot if you haven't been using it, that most of our metrics from here gets pushed onto the CloudWatch, where you can monitor lots of things that are going on with your training and cloud simulator, and you can debug your model, and you can start this cycle. From day one, we decided that it's really important for the developers to learn that their model is doing the right thing. If they want to do an early stop and reconfigure their environment, they should have the opportunity to do so, because that's what we learned while we were building this unit test. Very important. There are tons of resources, as I mentioned. You can go check out the DeepRacer Slack community, GitHub. There are lots of free videos to get started. And I would really appreciate that once you find bugs or once you find new ways of doing and using DeepRacer, I would like to hear from it. And also, I'm part of the Slack community, and I monitor it quite frequently to see and learn about what other people are finding about AWS DeepRacer. And finally, if you really would like to get your hands dirty and that you are a machine learning AI practitioner, and that you had now some experience with AWS DeepRacer. In the past, we had run a NeRPS competition from which you had one video. And we also had worked with AI Crowd last year, and we had run and supported another NeRPS competition, which was mostly on software. So there are tons of resources for you to go learn about deep reinforcement learning, whether you want to use AWS SageMaker Stack, which is not DeepRacer, but it actually uses the very same tools as DeepRacer, except for a different environment. In this case, it uses OpenAI ProGen benchmark. But if you are really committed to giving us and finding out bugs and also learn about reinforcement learning, get some cash prizes, credits. We are currently have an ongoing NeRPS competition. There, when I copied this, there were 25 days left, which was last week. So there today, I think 17 days left to participate in this competition. So I strongly encourage you that you could go to NeRPS 2021, check the code space that we had provided. This competition is going to be in 2 rounds. The first round is going to be in software. The second round is going to be on hardware. So I strongly encourage that if you want to go to some hands-on work, get your hands dirty, and give back to the community on how we can improve software, hardware gap for these AI ML applications on device. I strongly encourage you to test this DeepRacer challenge. And you can actually run this locally. You don't have to have AWS services. We had it so that it's open to a larger community and that you can do things in a more complex environment. So with that, I'm going to stop. We have about 15 minutes left, and I will stop sharing, but I'm going to stay here to answer some questions.
Thanks a lot, Sahica. Guys, do you have any questions? You can unmute yourself and ask directly if you want. I see from one of the community members a suggestion that this competition might be appropriate for first technical challenge for middle school, high school students. Is this something that you guys consider?
Actually, 2 years ago, when we were actually doing in person, that I did a presentation for Sacred Heart Academy students, and they were middle school students. So the NeRPS competition is probably a little bit high level for them. But the AWS DeepRacer, where they can design reward functions, they really picked up on it, and they were really good. So I know for the middle school that it can be done. And they're actually, over the last year, several of my colleagues and solution architects really took this to several other middle school, high school students, and there are kits available. I'm not really sure about the discounts, but if you're interested in holding an event for middle school or high school, please contact me at my first name at amazon.com. We could definitely have you get started. I haven't done it over the last year, but I have colleagues, and there has been some blogs posted online, so you can also go and search for AWS DeepRacer High School. You will see that. I recently saw one that was done in US. I actually recently saw another one that was done last year in France, and they told me they're actually going to do another one this year. It was very successful.
Awesome. I'm wondering, did you, while working on this project, are there like any unexpected insights that you encountered that, like you didn't anticipate, but you sort of was surprised to find out?
Yeah, friction. So we learned that, so is you were saying that earlier, that we were thinking some physics is good, but not all physics is good. That didn't turn out to be the case. So we just moved into the cloud simulator, and then we realized that none of the things that we trained in our previous simulation environment was working. And we were like, the car is the same, and the only thing that changed was the simulation environment. And we have actually an exact model of the car. So then what we realized was that there was a difference in the physics package from what we were using locally to what we switched to when we started running it on the cloud simulator. And even this simple thing, what was happening was it was changing the speed of the car. And because our simulator was not training with the right speed of the car, which was in the actual hardware, we had this mismatch. And we didn't realize it was because that there was this one component of the friction forces that has changed. But if we didn't know about, if we weren't doing tests on, if we weren't doing hardware tests, we didn't know. The other one was this, on our device, we have OpenVINO, which was what I mentioned, that we built OpenVINO libraries and we're comparing the neural network. We did some tests with ResNet, for example. We put an image, we looked at the outputs, the neural network seems to be fine. But when we started running the neural network on the actual car, we were seeing these probability fluctuations, and it didn't make sense. And actually, my colleague Sunil, he said that, we really need to go down to the basics. And he actually put a napkin on top of the car on the camera. And the fluctuation in the probabilities were still there. So we were like, oh, there's definitely something wrong. So that from day one, we learned that no unit test is too simple to do. Always make sure that you have a good set of unit tests, and also range your unit tests from starting very simple to complicated. Sometimes the complicated ones, they don't actually give you the basics that it seems like in the AI ML world, it does look like it is working, but always break it down to multiple experiments, vary the complexity of it, and make sure that your device and or software passes those tests.
Yeah, that's what's very interesting to learn. Thanks for sharing. Can you talk about AWS RoboMaker? Sachin,
yes.
What do you mean? What exactly do you want to learn? I'm just asking the person who asked this question.
Right. So I see that RoboMaker is the foundation for DeepRacer. So I run a robotics club for the FTC and FLL, and I'm seeing if there are other use cases that we can do just apart from the racing part of it. So that's the question.
Yes. So actually, last year we did. Last year we open sourced another set of code where you can have DeepRacer do how you can actually use DeepRacer at home, because as you can imagine that having to have these huge tracks at home was not very viable. We started doing something called underground races. There were a few people and they had basements. They actually set up tracks, and they started a community where you can actually send your models to them. And I actually have tracks at home as well. So But what happened was that we really wanted to reach a bigger community. And if you actually look at AWS DeepRacer ROS 2 resources, sorry, I actually sent a message I should send to everyone. So if you look at AWS DeepRacer, if you search for ROS 2 resources, you will see that we open source the code on the hardware. Our hardware currently uses ROS 2, and it matches our ROS nodes in RoboMaker. And with that, you can actually now, and we put some sample applications where you can have DeepRacer navigate in a house environment and several other applications. They're all open source. All the resources on AWS DeepRacer, by the way, are open source. There are a lot of GitHub libraries that you can utilize. Got it. I may not be able to have access to some of the things that are happening in the Slack channel. I would really appreciate if you can reach out to me via email in case I lost track of this. I would really appreciate it.
Do we have other questions? Sahica, maybe can you share what are your plans, how to push forward this research? What are you planning to do next?
Yeah, so what we had done in terms of research-wise, we actually take this and we started working with actual customers. So if you look for, you will see that I have a blog post with Woodside Energy, where they started using these kinds of different kinds of approaches in their robotic applications, where a mobile robot with arms would go into a plant, power plant, and they would perform operations, whether in the absence of humans and or that when it is not very safe for the humans to get closer to the valves of a gas turbine. Other applications that you will see that we had posted several blogs working with customers who are putting this in production. And I also provided a talk at Ray Summit this year, where another application was in manufacturing, how you can apply it to robotic arms. So we're currently the team, currently the team is looking more into how can we take this kind of a toy problem, which actually came up with not so toy challenges. Then we start working with our customers and how we can help them. So that was the direction that we took in terms of putting this in production. The second direction that we took is we learned tons from interacting with our community. One thing that we learned was, and this is actually related to another question I'm seeing here, that how expensive is it to train the models? Training the models currently, I think it just takes a couple of dollars. We really narrowed it down for you. We find the best hyperparameters that you can use to cut costs on this. And so another thing that we learned, however, is that we were at Mars, and we had a couple of day racing going on. And some of the developers and solution architects, they were coming to me saying that, okay, since this is a couple of days, I want to test my model today, and then I'm going to upload this model, and I'm going to do a kickstart, right? So the next day they come in, they use the model from they test, for example, 3-4 models on the actual track. and then they pick the model that works, and then they kickstart next training using this model, which takes even less time. And they were getting really good results. So we started going back to the drawing board and said, how can we actually enable our customers that we can transfer not only from track to track by cloning their neural networks, but also from different reward functions. And so we actually developed a new way of transfer learning for reinforcement learning, which we call repaint. And we have a paper published at ICML. So first, it started out with this community, trying to help the community reduce the cost. And then we actually went out and we built a theoretical foundation for it and showed how it can be done and how it would actually converge in theory. And then we also applied this to other problems. As it turns out that we are really good at StarCraft. So our approach transferred learning from different maps of StarCraft to different reward functions, and it just was learning things in a couple of minutes. We were really surprised. So as you can imagine, that this is an opportunity for people to learn about not only machine learning, but because we made everything available open source, from simple code to more complicated code, and decouple it, you can basically go back and forth between using this for your, let's get started, very simple, let me learn about reinforcement learning, and this is a very simple robotics platform that I can start, but it has actually answers to some complex problems that you can rate in the real world. And this is really what the direction that we're going so far.
Sahica, do I understand correctly? So basically you have different customers, they have somewhat different use cases, but when you deploy your models into production, there's not much adjustment, in a sense of like reward function or like other parameters. Is that right? I'm just curious, what customization do you do for customers when you deploy those models?
Yeah, for customers, they would like to bring their own simulation environment sometimes. That you can do that. And some of the customers already have their simulation environment, for example, in RoboMaker, and then we help them with the reward function. And in some cases, we work with them we provide consultation for their reward function simulation environment, because each customer, there's nothing that fits one all. While this tool set, we have it for AWS DeepRacer, it is pretty extensible. So they can bring their reward functions, they can change the reward functions, they can change the neural network, and they can completely take out the simulator and put another simulator. GE, for example, has been using PyBullet instead of Gazebo, which is provided in our cloud simulator.
Okay, gotcha. I think we can wrap up for today. Thanks a lot for your time and for this amazing talk. Just a reminder, the video will be available probably in a couple of weeks, but it will be definitely available, and I will post in our Slack. And also, Sahica, please share all materials that you want me to share with our community. I will make sure that I will post it in our Slack channel. Thank you very much. It was a pleasure to have you today.